Okay, let's go ahead and get started. Going to just start actually today by looking at some of the answers from the online quiz. There was some very useful information from there. So we go right away. This came up in the any questions section on the quiz, and I thought it was a very useful comment. It had to do with questions from the first lecture. Starting off with the intentional trick questions, it concerned me. Yeah, it would concern me too. But I just want to highlight something here in this regard. There really are no trick questions in physics. There are hard questions, and there are ones that are not intuitive. And the question, for instance, about the ball at the top of its throw could be viewed as a trick question, and I would understand that. It's not, because there's no sneaky answer. It's a very clear-cut physics situation that's not intuitive, and because it's not intuitive, it can be hard. On the pre-quizzes, and especially in lecture where you don't have to do it for credit, I try and do as many of these as possible. That is true. And that is why I started the class with one of these. Why? Because if you do not know when your intuition is going to fail, it makes it that much harder to study for this class. So the more I front load you with the obvious, and like I said, I've done this for 16 years. I know what students don't understand. I know what you're going to get wrong. I try and make sure you get it wrong in class, in lecture, or maybe on a pre-quiz that's only worth a few percentage points of your grade, so that you get it right on the exam and the final. So pay attention. If you feel something was a trick question, that should be a warning sign to you to say, there's something I don't really understand. It's not intuitive for me. I better make sure I get that down. Make sense? Excellent. Now, I love this one. I love this answer. First of all, you notice I actually read the quizzes because, I'm taking direct quotes. And the two of you who wrote these, if you show up to class, know that. I know what velocity and acceleration are. I'm not sure what velocity and acceleration are in terms of physics. This is the same very much. It's very similar to the previous issue, right? Where it's a question of what's your intuition. So there are occasional words, and they're on your sheet. That's why they're on the two concept sheet, that do have a very specific definition in physics. Now, your intuition is not quite as bad as you would think. Which would you rather buy? The car with a top speed of 200 miles per hour but goes 0 to 60 in 3 days? Or the car with a top speed of 100 miles per hour that goes 0 to 60 in 2.9 seconds? Which one would you rather have? Well, there's not a right or wrong answer. You might like accelerating really slowly. You might view that as safe. But you know what acceleration and velocity are. You just forget that, and you're not usually careful with them. So the biggest thing is acceleration is your change in velocity over some time period. It's 0 to 60 in X seconds. And that is the piece. It's not velocity. It's change in velocity. It's related to velocity. And so when you go to the quiz, you want to be thinking that. Well, first of all, in the quiz, pretty much everybody knew the units of mass. Excellent. Most of us got, again, the relative velocity problem right. We're comfortable with velocity. We're comfortable with the idea if a train's going this way and something's thrown this way and you're watching, I add those two. And it looks faster to me. Most people got that. Few of you got a little panicked worried about the trick questions and thought, well, what's really the front of the train and which way is it going? I mean, there's times we just use normal English. The train's going forward, I'm walking forward, that's the same direction. Right? There's no deep things here. If the train was going backwards and I was walking forwards, you would know what I'm talking about. If the train's going backwards and I'm walking backwards, you'd know what I'm talking about. So sometimes we use normal English. The other one, and this is what's interesting, definition of acceleration, everybody mostly got it right. You looked it up. Some people noticed they forgot the time issue. Okay? It's velocity divided by the time to make the change. But then, this is where it got interesting. And this is what I mean by, this is where physics gets hard. And when I said yesterday, or on Monday, that the first step is to just memorize and use the definitions without understanding them. Don't get me wrong. If physics was easy, it would not have taken until the 1400s and Galileo to finally figure out how to describe motion. Okay? A lot of smart people lived before him. So if you don't get it right away, you're in company with a lot of smart people. It took a super, super smart person in Galileo and Newton to finally figure it out. Now that they've actually explained it, it's a little easier for us less smart people to understand it. And again, I recognize I've been doing this for my whole life. Obviously, this all seems obvious to me, and it's new to a lot of you. But it is about just being careful and taking the time. You all pretty much got right that velocity, acceleration was change in velocity. So, if I were to ask you, okay, if your velocity is 0, what's your acceleration? Your immediate response has to be, there is not enough information. Because I need to be able to compute a change in velocity if I want to have any chance of finding acceleration. Right? The definition of acceleration, you got, it's clear. Change in velocity divided by a time interval. If all I have is one velocity at one time, no information about time, no information about change in velocity, there is no decision I can make. And that's the only conclusion I can really come to. And that's the practice you have to get. And trust me, if we go a little slow this first week and then we pick up the speed a lot, but if you can get down velocity, acceleration, and position, the vectors and how those definitions work, and the logic of how it works, then everything else is basically the same, just with sort of new situations, new words. The logic doesn't change much. So this is the week to really get that logic down. Any questions on those things from the quiz? Excellent. Everybody now understands it all. So, we're going to do, oh yes, oh a question, yes.
So, for the train, the person, it would be 78 because the person, it would be the person looking at the train?
Yes, the question was clearly much for you looking at the train, how fast you see the object moving. And we're going to do more of those today. That's why we have our river and our car crossing the river. You would think it would be a boat going across the river, but we use a car. It's a very shallow river. And a very light car. Other questions? I would like to very quickly now cover chapter 1 in about 5 minutes. So the first thing, a couple people brought this up on the quiz. I didn't bother to put a quote up. Significant figures. Now, here's a warning. If you plan to take the MCATs, they probably care about significant figures. If you're going to take more Physics 3, your other professors might care about significant figures. I don't. But, that being said, your homework cares that you're close enough to the answer. I think you have to be within like 1% of the answer. And I don't want to see 7 irrelevant digits. You know, don't just copy your calculator down. Okay, that's not what we're going to do. What I do want you to be able to do is use a reasonable number of digits. Okay? What does that mean? You know, if numbers are given to you with 1 or 2 decimal points and you do your calculation, yeah, it'd be nice to use a decimal point or 2. If you're off by like 1 significant figure, am I going to notice? No. Be aware, mastering physics, if you round too much, it will tell you your answer's wrong. It's working to within a certain window. So there, keeping track of significant figures to the best that you can does help. Again, MCATs might care, next semester might care. Not something, there's a lot more we have to worry about. So I won't be worried about it. What I will be worried about are units. This is something students tend not to believe when I say, but on every exam and every problem, there will be 1 point for units. This is such a hard and fast rule that sometimes my TAs don't get it and they have to regrade the entire exam when they grade it wrong. This means, if the question says, I go running off a cliff, what's my speed when I hit the ground? And you have no idea how to do the problem, and you write in the box meters per second, because that's the units are for speed, guess how many points you'll get? 1 point. If you do the whole problem right, and you write 6, guess how many points you'll lose? And it's worth 2. That is how important units are. You make a mistake in units, you kill a patient. It's that simple. You give them milligrams when it's supposed to be, grams. That's maybe not so bad, but you give them grams when it's supposed to be milligrams. That can be quite bad. Units are critical. You make a mistake in units, and the interstellar probe you launch doesn't quite go where you expect it to go. So unit mistakes are a big deal. They matter. They tell you the physics. They tell you what you're doing. Now, do you need to use meters per second? No. You could use centimeters per second. You could use meters per hour. They just have to be the correct units for the physical quantity that is being asked about. Any questions on that? So that means if there's 10 short answers on an exam, and they each have a question that has units with their answer, what's the lowest score you should get in my class on that exam? 10, because you should know the units for everything and go through and write it down. Good. Now, the other thing that you just mathematically, that's in chapter 1, that you want to make sure you're familiar with if you're not, and most of you have used this, you're all bio majors or chemistry majors, mostly bio majors, you've used this somewhere. Make sure you're comfortable with scientific notation. We just use it a lot. I'm not going to go through it. It really helps. We use big numbers, we use small numbers. Know what your 10 to the third is, 10 to the fifth. Know what milli, mega, kilo is, all of that. And something we don't really do in the class, but is worth thinking about, and I'll occasionally do, is think about how big stuff is. I told you, this is about the physical world. It's physics. It's real stuff. If I were to ask you what's kind of the approximate top speed of a human being running a short distance, anyone have a guess in meters per second what that might be about? Just is it 200? Is it 0.5? Is it 1? Is it 10? Is it 100? So what's a common race in the Olympics? Has anyone watched the Olympics? Okay. The 100-meter dash. What's the world record for that? Something about 10 seconds. What's 100 divided by 10? 10. Fast speed for humans, 10 meters per second. There you go. There are things, about how big is a football stadium? Yeah, now, maybe it's 200 yards. You got to fit the stands in, right? The field's 100 yards. So you know how big stuff is. You know how fast things go. Believe it or not, you really do. How many days does it take the Earth to go around the sun? 365. Hopefully you know that. How many hours does it take the sun to rotate? Not the sun, the Earth, sorry. Yeah, the sun's a trickier one. How many hours does it take the Earth to rotate? 24. So don't come to the TA and say, the problem, I need to know how long it takes the Earth to rotate on its axis, and it's not in the book, I can't find it. That's something the book expects you to know. So those are things from chapter 1. We're done. Any questions on chapter 1? Excellent. Moving on to chapter 2. Now it gets interesting. What we're going to be doing now is describing motion. And like I said, we go a little slow at the beginning and then we really pick up pace. And part of it is to really drive home the importance of not just knowing the definition, but then using it in a careful and logic fashion. And in describing motion, most of what we deal with are simple definitions. But our main goal is to know where are things and where are they going to be. These are the two fundamental questions from the dawn of time because you really, really wanted to catch and eat that rabbit. So you needed to know where the rabbit was, where it was going to be, so you could make sure your stone, rock, spear, arrow hit the rabbit where it was going to be, thus getting dinner. Most of you do not have to worry about motion at that level, but you asked for a practical application, some of you. So if you're stuck in a survivor mode in the woods, this is where physics comes in. Solving how to hit the rabbit with the rock. Now, a lot of that's hardwired in, so those are the easier sort of problems to solve. But in the end of the day, what it comes down to are collisions. You'll see almost everything we do in Physics 3A comes down to two objects or more interacting in what we would broadly call a collision. So we get to do our first clicker question. So get your clickers out, get ready. The most, did it start? Yeah. The most general description of a collision, oh, I started and I stopped it. There we go. The most general description of a collision or impact is when two objects are at the same position, when two objects are at the same position at the same time, when two objects hit each other, when two objects interact with each other, both C and D. Notice I put collision and impact in quotes. We'll give you like 10 more seconds. And done. Now, a lot of you went with C and D. Very few of you, well, it was reasonably split between B, C, and D. If you look at what I picked B. And this is one, yeah, I know, you're all upset now. This is one that won't be on the test in this form. But the reason is, in this class, a lot of times, we'll have two objects that really aren't necessarily interacting or hitting each other. Now, most of the time, collisions really involve things actually hitting or interacting. But a lot of times, because objects in physics, we do make some approximations. And you can have two things be at the same place at the same time because we imagine them to be points with no real spatial extent, and they're not really hitting or colliding or interacting. But it's still treated as a collision. And from a physics point of view, to solve the problem, the physics information you need to know is that the two objects are at the same position at the same time. That is the number one thing. Any questions on that? We'll come back to that one. So what we're going to do in describing motion, there are three things you need to know. Number one, you need to know an object's position, which we will often talk about its displacement. And we will often talk about distance. These are all related to the question where. They're slightly different. They deal with slightly different aspects of where you are, but we use all of them. At the next level, we will deal with speed and velocity. These both have to deal with how fast and where are you going. It's interesting. We have three words at the top, two in the middle, and then the last one is acceleration, which we already saw has to do with changes in velocity. And that's it. Those will be the three items. Once we know those three things, we'll have completely described the motion of an object. And that's what we're going to want to talk about today. Now, in doing that, we have, I'll leave that up there for a second, we have basically two concepts we use in describing that. We have what we call the frame of reference, and related to that is our coordinate system. So that naturally raises the question, which will be our next clicker question, so think about that. As I'm walking across the room here, how fast am I going? That's the clicker question you want to answer, so let's pull that up. How fast am I moving right now? And we'll start it. So we'll answer it now. How fast am I moving? And 5 more seconds. 3, 2, 1. Let's see how we did on this one. Over half of us went with it depends, you're learning. Right? That no question really has an answer. We're teaching you all the wrong stuff. But this is one that truly does depend. Actually, in reality, you will learn I am the center of the universe, so the answer is 0. But that is what we mean. At the end of the day, when it comes to describing position and velocity, it was really an amazing breakthrough. And a lot of people had thought about it, but it really was Galileo who realized how important the frame of reference was. And what it comes down to is position and velocity are relative. In the following sense, the numbers, okay, this is important, you use to describe them do depend on your coordinate system and on your frame of reference. So these two things determine the numbers. And we're going to look at a couple of examples at how that works. But that's the number one idea. And even though what's interesting is right now, if I were to ask you what is my position, it's pretty obvious. I'm here and you're all there. Right? I have a definite position. That's not in question. But the question is, what number am I going to use to describe my position? And that'll come down to coordinate systems. Any questions? Actually, I will just start this on a whole new page. So let's draw a couple of coordinate systems. So in physics, because I'm always drawing on paper, everything is almost always in 2 dimensions. And we like to use x and y. And I'll use the little sub 1 to represent my first coordinate system. We like coordinate systems where the axes are at a right angle, so that's at 90 degrees, because then we can use trig and components, and we'll see all of that later. But there's nothing to prevent me from not maybe tilting my coordinate system. So this might be a second one. And there might be times where that is incredibly useful. And there's also nothing to prevent me from perhaps having my coordinate system down here with a different origin. So if I look at this one we would describe as having a different origin, because the origin's where you're at 0, 0, and these two are described as rotated. Now, what I might want to do is discuss an object sitting here at point A. Where is my object at point A? Well, if I use coordinate system number 1, now I haven't drawn little hash marks, right? But suppose I did, I might do 1, 2, 3, 1, 2. So it's at position 3, 2. That's its x coordinate and its y coordinate. Now, in coordinate system number 2, however, clearly it's somewhere else. Notice it's way out here on the x-axis. Very different position. And it might be at 4, -1. Notice if I draw a line over here, it's at the negative y-axis for this rotated one. So that's radically different. I've gone from a positive y to a negative y by rotating the coordinate system. Very different number, same exact place in space. And now if I go to number 3, I'm maybe at 1 and 8, right? Because it's a much longer distance up here than in any of the others, because I've moved the origin down. Make sense? So again, the main point, the numbers could matter. The numbers will be different depending on where you pick your coordinate system. But the point is at the same place in all 3 cases. Its position hasn't changed. Just the coordinate system I want to use has changed. Now what's interesting is if I take another point, say, and stick it over here, point B, and I draw an arrow between the two, now I have a displacement and my displacement I write as delta x. This is telling me about that there's something that's a change going on, and I write it as the position of B minus the position of A. And if I were to look at this, in all 3 coordinates, now I would actually get the same answer for the 2 that are shifted. Actually, I get the same answer for all of them. Because, let me say that again. I would get the same answer for the length in all 3. This distance here, What would be different between the rotated one and the one that's not rotated? The direction. Okay, and how do we see that? So if these are my two coordinate systems, and I want the displacement between this cone, and this is x and this is y, what direction is it in? X. If this is x and this is y, what direction is that in now? Somewhere in between, like maybe 45 degrees from x. Right? So if I rotate, I can change direction. If I shift, I'm not changing anything. Even if I rotate, the length I get will be the same. So let me write that down. We'll just summarize that here. For the displacement, the length stays the same. The direction changes if I rotate the coordinate. So that's something you want to pay attention, and that is why this right here is one reason we like to rotate our coordinate systems. Because sometimes we'd like to use the direction to just be the x direction or just be the y direction. So we'll draw our coordinate system specifically to achieve that. And that's why it's worth remembering. Any questions on this starting point with coordinates? Yes?
Delta y doesn't really matter.
So remember the length, notice, oh, good question. I should have said this. I am already mixing in the fact that we're dealing with vectors. So I drew the arrows. So this x is not the x direction. And this is a very common physics thing, and it often leads to confusion. X with the arrow is the full vector. We're going to say more about this on Friday. It's the full vector with magnitude and direction, whereas x without the arrow and y without the arrow are our coordinates. So when I write delta x with an arrow, that's the entire thing, and it contains both the change in the x coordinate and the y coordinate. And I know that language can be quite confusing, but it's a common thing. Sometimes you will see, to avoid that, you will see people use r here, and then they'll use delta r. And that helps a little bit with the confusion. Other questions? So that's basically our coordinate systems that are stationary. Now the other thing we can do, our first question, we started this by asking how fast am I moving. So the other thing we have are moving coordinate systems. So we have our river, which is this nice piece of paper, and we have our boat. And our boat moves in a straight line. Yay! And it gets across the river. And notice we had a collision. Our boat and our cone were at the same place at the same time. Now, oh, this is interesting. Okay. Can I have a volunteer to start my boat? And then you'll sign the video waiver later. You okay with that?
Yes.
Good. Okay. So now our river's going to move. So go ahead. It's the metal switch. Just switch it to start.
No?
Sure. I didn't do that very smoothly, but now we had a different collision. You can go ahead and stop it. Notice a couple of things, and we're going to do this again, if you don't mind. Which direction, relative to the water, from the water's point of view, did the boat always go? Straight across. You could tell because it was pointed that way. That's what gave it away. Which direction, relative to you, did the boat travel? Diagonally. So let's do it again. Go ahead. And boom. Okay? So we have two frames of reference. Let's give our demo person a nice round of applause. Thank you very much. We have two frames of reference in this case. This is a little trickier than the quiz question, right? On the quiz, the online quiz, we had a train moving in some direction. Oh, let's make the train bigger. We had a train moving this way, and we had a ball inside the train moving forward. And we asked questions in the frame of reference of the train. I believe the ball was going, say, 3 meters per second. In the frame reference outside the train, just stationary on the earth, the train was going, say, 75 meters per second. So, relative to outside, the ball went 78 meters per second. You all intuitively had the sense of adding those two numbers. With our river, it's the same thing, right? We have a river, and we use notations like this. The velocity of the river, so R for river, relative to the bank, which is the side of the river, was some value. That's the river moving. Okay, here's the bank not moving. And then we had the car. Notice, see, I use a car because its first letter is C. If I use a boat, its first letter is B, and then bank and boat have the same letter, and I get confused. So the car has some velocity of the car that we did relative to the river. Right? It was moving relative to the river in that straight line the way I just drew it. Right? So I had the velocity of the river relative to the bank, the velocity of the car relative to the river going across, and then when I added the two of them, I got the velocity of the car relative to the bank going at an angle. And this is your first lesson in vector addition. We're going to do it quickly now and then come back to it in detail on Friday. But notice we start with the tail, the head, and then the other tail, and the other head of the vector, and then we connect tail to head. And that's how we add it vectorially as a picture. It's the best way to first do it. The other thing we would write is the velocity of the river relative to the bank. I'm sorry, velocity of the car relative to the river plus the velocity of the river relative to the bank is giving us the velocity of the car relative to the bank. And that's what we mean that's why adding velocities is the same as changing our frames of reference. And there's a little trick. If you notice, I was very careful to label everything velocity of some object relative to the frame. Because when I do that and I write the adding, there's a little trick. As long as those two are the same, they cancel. And these two tell me what my answer will be. Notice CB, car relative to bank. So it works out. Now, occasionally you have a situation where what you know, so maybe you knew the velocity of the car relative to the bank, and you knew the velocity of the river relative to the bank, and you want the velocity of the car relative to the river. Well, these are not in the middle, they can't cancel. All you have to do is remember another rule is if I switch, I put a minus sign, right? Because if I think I'm moving this way relative to you, then relative to me, you're moving that way. Right? Two things moving relative to each other are a minus sign. So if I'm walking this way, and I'm saying my velocity relative to you is in this direction, if you were to ask me what's your velocity relative to me, it's that direction. And in fact, there was a great example of it yesterday. My daughter is 16, learning to drive. She was parked, and there was a big city bus next to us, and there was a red light, and the bus started inching forward, and I swear I had the same effect. Both of us thought the car was moving backwards. Right? We had no frame of reference. It's also a hybrid, so the engine's making no noise. So you can see, and her foot's on the brake, and she screams at me, "How do I stop going backwards?" Because there was a car behind her. You know, she thought she was going to hit it. But that's that relative motion experience. And we've all had it at some point. And this now saves that problem. It's the minus sign. And now I have the car relative to the river. Any questions on that? Excellent. We are now going to do our example problem. Now, one thing, I forgot to do it. I apologize. And I will do it for the rest of the lectures. So you don't have to write all the words down. I like to post all the examples I'll be doing in lecture ahead of time. I just forgot to do it today. You know, it's early in the quarter, my brain's not working yet. So in general, and this will get posted tonight, so if you don't want to write down all these words in your notes, you want to just use it, that's fine. If you want to write them down, go ahead and write them down. But the question is, we got two male deer out in the woods. You've all seen the nature videos. They're going to fight, so they're going to run at each other and headbutt. Now, this is a fairly simple one because they're running at the same speed, but it's going to be able to introduce some concept I want to show you. They start 20 meters apart, they run at each other, and they're each going 5 meters per second relative to the ground, and you're asked how long does it take for them to collide. What are we going to want to do? First, identify the question. How long? So our answer better be a time. So in your find box, you're going to be doing that. How long for what? For them to collide. You see that word collide, you see collision. You're immediately thinking they better be at the same place at the same time. Even though this is one of the simplest physics problems you'll face, they only get more complicated, and I can tell you this. I don't know anyone who's ever solved a physics problem by looking at it and immediately seeing the answer. Very rarely can you answer it in one step like that. What you have to do is pick apart the pieces and answer each piece and then work your way backwards. Having said that, what's the situation? Well, they're 20 meters apart, so let's draw that. 20 meters. We'll have deer 1, deer 2. I can't draw deer, so I'm not even going to try. And they're each moving relative to the ground 5 meters per second. How are we going to solve this? Now, what I want to do is very quickly take you through 3 different ways you can solve this problem. To right off the bat show you that depending what you think of, you might solve it differently, and all will give you the same right answer. So let's switch gears now to the, to where I can write. So the first thing you might recognize is nothing about the problem. And you might do it what I will call the long way. What's the long way? Well, I have deer 1, I have deer 2. Deer 1 travels some distance x1. Deer 2 travels some distance x2. I know the sum of these is 20 meters, because I was given that. I also know one concept. I know that distance equals speed times time. This is my one concept I know. It's really a definition of velocity. I know what I'm looking for is time. So I know the first one travels sometime t times its speed, and the second one travels sometime t times its speed. For both of these, I know t is the same because they start at the same time. And by definition, I already established that the collision is at the same time. And notice, I didn't have to tell you they get to the same spot at the same time. All I had to tell you was that there was a collision. And that's how you know it's going to happen. Having done this, and I'm going to put the math up later, you can plug it all together and find that time is 2 seconds. Now, you have another way of doing this, which I will call the frame of reference way. And what you do there is you say, okay, let's take it from the point of view of Deer 1. In Deer 1's frame of reference, how fast is Deer 1 moving? 0. I'm not moving. Okay? But Deer 2 is now moving 10 meters per second at me. That's what it looks like. If we change the frame of reference, because we're going to now solve for the velocity speed of Deer 2 relative to Deer 1. I will probably do that quickly at the beginning of the next class, but we have only 2 minutes, so let's finish this fast. We are 20 meters apart, so Deer 2 will get to Deer 1 in 20 meters divided by 10 meters per second, voila, in 2 seconds. The same answer. Now, the final one, and this is what we'll end with, is what I call symmetry or the shortcut. Where do they have to collide? Where do they collide? They have to in the middle. Notice, this is the hardest one to use because you better be darn sure you recognized it correctly. But in this case, if they're moving at the same speed, they've got to hit in the middle, right? So they hit at 10 meters going 5 meters per second, so they hit in 2 seconds. So 3 different ways to do it, all get you the same answer. I know they went fast. Most examples will not go this fast. What will also happen with the examples is you'll see a careful solution posted on the web, and I'll hit some of these points to start us off on Friday.